Welcome to Spring LIB.
In this problem, we're looking at a structure with the molecular formula C10H13NO2. So here we are given IR and NMR data to find our structure. So if we look at IR first, notice that around 3300 we have a peak. That's a nitrogen-hydrogen stretch. And because it's a singular peak, it means this is going to be a secondary amine or amide. And around 1600, we have a strong absorption. Those are for carbon-carbon double bonds. Around 1200, we see an absorption. That's a carbon-oxygen single bond. So we expect an ether or an ester or an alcohol, but because we don't see an alcohol peak, we can rule that out. So then if we move to our NMR data, you'll notice in the 6 to 8 parts per million range, we have two really nice doublets, and we see that when we have a para-substituted benzene ring. So we have two hydrogens on each side, each has one neighbor, making them doublets. And we also see a one hydrogen peak in between those. This isn't aromatic, it's actually the hydrogen on nitrogen. So then if we go back to our NMR, you'll notice at 4 we have two hydrogens that show up as a quartet. So usually when we see two hydrogens as a quartet, it means we have a CH2 group next to a CH3 group. And for where it is, this is either attached to oxygen or nitrogen. So it would be hard to tell in this case, but it is an oxygen. So we have an ether at one side. And that leaves us with 3 hydrogens. And these are shifted in a range where they would be next to a carbonyl. So here we're going to have a carbonyl. Here first we have our nitrogen with our hydrogen. And then we have our carbonyl, and then our CH3 group. So there's no neighbors, which is why this is a singlet. And it's shifted so it's next to the carbonyl. If it were attached to the nitrogen, it would be much further downfield. So this is going to be